Okay. Morning, review day. So what I've done, and I guess I should have taken that time to download a fresh one because the one, so I downloaded the practice test just kind of as a PDF. I realized I shouldn't have had the ones with the answers beside it, but it doesn't matter, whatever, we'll just ignore them. Um, Maybe it's nice to have them on the side, but I
Ultimately,
think
we're trying to find how to get to there.
yeah, it's like, we made it. Okay, great. Um, I think you guys are able to download like PDF versions, but I don't know if they would look like this. I don't know. For me, it's just easier to have like a compiled version, but it doesn't matter. Okay, so of course we've got our first test number 1 on Friday. Hopefully for you, it's your last midterm before the break or your last test before the break. Don't have class after. On Friday, it will be available on WebAssign. On WebAssign, right at 10. At 10 until 11:50, okay, which should be plenty of time to do it. I gave you that practice test for an idea of the length and the types of questions to expect. I'm keeping it pretty similar, so if you're able to kind of handle the practice test, then that's great. Then you should be prepared. I did put a bonus question on the test as well, but it is just a bonus question, so for 1 mark. So just don't be thrown off. The last question is a bonus question. And then I'll give you, just to not cut into your writing time, although like I said, you shouldn't need it, but I'll give you an extra 10 minutes. So upload your work and all answers. I will say that because especially in my other class, people are refusing to just give me the answers. I don't know why. It's insurance for you guys. You two are fine. So so upload your work and all answers to Gradescope by 12 o'clock. So I'll give you that extra 10 minutes and that should be fine. Okay. Let's see here. Any questions before we get started? From you guys? No. All good. Cool. So because we have time, I think we should just go through each of these questions. I know some of them are quite easy, but let's just go through them kind of one by one and pick away at them. And there's only 15, so let's do it. So I guess I should start with the ones in the back. No, I feel confident that we have enough time to go through all of them. Otherwise, I should start with the newer ones, but nope, I refuse. Okay. So here we have practice test number 1. And we'll just go through each of these. Of course, your numbers might be different, or your numbers will likely be different. But at least this way, we're kind of referring to the same problems, right? So here, right, I guess this one's not random. on my end, the random numbers show up as red, so that's what we'll see. But, okay, so we want to find the difference quotient. The difference quotient is this, right? F of a plus h minus f of a over h. And so typically when we do one of these, eventually the h in the denominator will cancel out, okay? And we're using this later on to use limits to define the derivative. So that's kind of where we're headed, is towards derivatives, but we've got a lot of kind of random stuff to get through first. Okay, so we have f of x and we want to find the difference quotient. So let's do it. So we have f of a plus h and f of a. And I know these can be a little bit tricky until you've done quite a few of them. So if you want to find f of a plus h and then f of a individually and then put them together, that's totally fine. I'm going to do them all in one go. So f of a plus h minus f of a over h is, so f of a plus h, I'm going to replace all my x's with a plus h in brackets, right? So negative a plus h to the power of 3 minus negative a to the power of 3 all over h. Okay. So what I would do, because my goal is to try my best to cancel this h in the denominator, just as a spoiler alert, later we'll take the limit as h approaches 0. So that's where this h in the denominator becomes a problem, because then we're dividing by 0, which we try to avoid, right? So we've practiced some of these already where we have to manipulate it so we're no longer dividing by 0. Right? So that's where we're headed. There is a reason I make you do this type of question. So what I'm going to do is usually I just expand things out, because when I expand a plus h to the power of 3, I will probably be able to cancel it with this a to the power of 3, right? And so, and then things will kind of shake out, hopefully. So I'm going to keep that negative outside. And then just to kind of make sure that I multiply that negative into a plus h to the power of 3, I'm going to do a plus h times a plus h. That's a plus h to the power of 3, right? And then it's plus a to the power of 3 over h. So I don't know, it's like I like to do work, but I do. I like tedious things. So I always just write it out and I expand it out. Right, first I'm going to expand out the first two, and then I'll expand that into the third one. So what this looks like is I get negative a squared plus ah, just to show that they're the same, plus h squared times a plus h plus a to the power of 3 over h. So I can simplify that, and then I can expand it out, right? So now I have 2ah in the middle here. And then I'm going to expand again. So, but I guess I should show those combined first. Be proper over h. Okay, so now I'm going to expand again. A to the 3 plus a squared h plus 2a squared h plus 2ah squared. I'm going to have to move this over because I'm running out of space quickly here. Sorry about that. And now I lost my place. 2ah times h. Okay, that's where I was. And then plus ah squared plus h to the power of 3, and then plus a to the power of 3. You don't want to stop writing your over h, right? I know it can, it's easily lost, but you have to keep it over h, otherwise change the equation. Okie dokie. So I can probably combine some stuff here before. So I see an a squared h. So I can combine these two terms, and then I have a h squared. So I can combine those terms. So what do I get here? I get negative a to the 3 plus 3a squared h plus 3ah squared plus h to the 3 plus a to the 3 all over h. You want to make sure that you bring this negative onto each of these terms, right? Not just the first one, negative a to the 3 minus 3a squared h. Oops, there I did it. Minus 3ah squared minus h to the 3 and then plus a to the 3 all over h. So notice after all that, negative a to the 3 and a to the 3, what I've done is I have an h term in each of these that I can pull out, right? I can factor out a common h and I can cancel with this h in the denominator. That is great news. So I have h times negative 3a squared minus 3ah minus h squared, if I pull out that common h, over h. And that would be my answer. It should accept that. They might have pulled out this common negative right out front. You don't have to. In fact, now I'm curious. No, they just kept it. That's great. And also, phew, it's right. Whenever I'm able to cancel the h, I'm pretty sure that I've done it correctly, right? It's when I run into, when I can't cancel the h, then I know I've done something wrong. Okay. Question 1, done. Question 2 is kind of a cute one. So here, like I said, these numbers, the red ones, will be different or potentially different for you, but the idea stays the same. So we want to evaluate this function, this piecewise function, at 3 different points, -4, 0, and 3. And so it's going to behave differently. It's going to behave like a straight line, right? This is a straight line, x plus 3, if x is less than or equal to -1, right? So it's going to be, I already know what this thing kind of looks like, right? Up until x equals -1, it's going to be a straight line with a slope of 1 and a y-intercept of +3, right? So I know I'm going to have this, this kind of situation here. So up until -1, I know I'm going to have this kind of, might look something like that, right? And then I also know, so if x is greater than -1, but not equal to -1, of course, then it's an x squared. So then up until that point, I might start here somewhere. I have this kind of parabola style. So I already know what this function looks like, right? I can calculate some specific values, but in general, this is what I'm looking for, right? And of course, we can just plug and chug. I feel like you guys are really quite fine doing that. So no big deal, right? You just want to make sure you're in the right piece of the piecewise function. So if x is -4, then then f of x is x plus 3. So f of -4 is x plus 3, which is -4 plus 3. -1, and I guess I have the answer there, so phew, it's right. Sorry about that, guys. It's like a spoiler alert. I have the answers in there.
These ones, it seems pretty much just pay attention to what the question's asking, because
Yeah.
especially with the identifying the graph bit.
Yeah.
With hilariously, when I brought it up on WebAssembly, and I got this exact one.
Oh, really?
Well, second time around, because I had selected the wrong graph. Because the less than or equals to bit.
Oh, okay.
The solid dot was on the wrong line.
Come on. So close. So close.
Very close, but yeah, when I redid it, I got this one, and it's like, okay.
Okay. Got this.
But also, the thing that was really throwing me off was I was looking at the x plus 3, and my mind immediately wanted to go like, yes, it's going up and to the right. Right for the straight line, but that's wrong, because every instance down or in the negative direction on the x-axis,
Yeah.
as the negative
Pretty
number
sure
for
like
y
this.
is increasing.
Yeah.
So
Yeah. I know. So picky. So picky. But I mean, at least it gives you the functions, but sometimes it's harder to pick the right one because you might miss like the tiniest detail. That's what I find. So like I'll usually do what we just did, where I just kind of like get an idea, and then I can eliminate some almost immediately. But yeah, it's still hard to see some minute details.
the solid dot, that's been throwing me off, admittedly, because
Yeah.
you probably noticed when skimming over the hand-in stuff of that I couldn't figure out where the when it was asking about the graph, and it's like, okay, the limit of this line here, and then there's the limit of that line here, and then there's a dot right in the middle. It was only after I ended up talking about that particular problem with my sister afterwards that I figured out, oh wait, it doesn't care about this one, it doesn't care about that one. Those two are the same. It's not defined at that point.
Exactly. Yeah. Yeah, we'll get to that one. But that one's like a little bit, it looks easy, but then you try to put the pieces together and it's like, okay. Yeah. I know. Yeah, that one took me a little bit to, I'm like, okay, trying to visualize it. Okay, so if x is 0 and 3, then of course we're greater than -1. So then x squared is our function. So 3 squared, which is 9. So I think that one's okay. I guess we could pick our function here. So here it's the open dot from the line. That's not what we want. This one has the parabola and then the line. That's not what we want. Here, this one has a line with a closed dot. This one has a parabola and then the line. So that's not what we want. So then, of course, this is the one we want. Okay. Oh, this one's kind of big. I'll do them kind of, I'll bring them in separately. Otherwise, it's this huge chunk of questions. Oops. So here, right, I'm just getting you kind of used to working with function compositions. It's also the question that I cut from quiz 1 because it was too long. So I'm just making sure that we cover all our bases. So okay, so I have a function f and a function g, and we want to find first f composed with g, which means g is going to go into f. And then we also want to look at the domains. Now remember, for function compositions, for the domains, you first have to look at, consider the domain of the function that's going in there. And then that function is going into f in this case. So the g has to satisfy the domain of f, right? And so it might be useful. I usually just kind of make a note and find the domain of f. Okay, just in general, x plus 4 can't be equal to 0, right? And so here, I'm not even going to show the work. I just know that x can't be -4, right? So anything going into f can't be equal to -4. Right, so here, oops, x is not equal to -4. The domain for g of x, though, is the set of real numbers, right? I can put any value in there, and there's nothing that's forbidden, right? And so for g, it's the set of real numbers, right, from -infinity to +infinity. So it's just nice. You don't need to have the domains, the individual domains, but it's nice to kind of be able to look back and just kind of use that as a crutch. So f composed with g, so part A, f composed with g of x, I usually like to write it as f of g of x. And then that's why I end up reading this kind of incorrectly as f of g of x, because it just helps me get here. It's actually f composed with g, but I mean, it behaves like f of g of x, so it doesn't matter. When I do these, usually what I do is I'll fill in g of x first, right? And then I'll take f of 7x minus 4, right? So then I'm putting in 7x minus 4 into f. So here, this becomes the same as f of 7x minus 4, right? Just replacing g of x with what it is. So then f of x is x over x plus 4. So now f of 7x minus 4 is 7x minus 4 over 7x minus 4 plus 4. Right? So this becomes 7x minus 4. And often I'll put brackets around that just to show that that's the one thing that's replacing x now. Over 7x minus 4 plus 4. Oops. So now we've built a new function. We can cancel some stuff here. 7x minus 4 over 7x minus 4 plus 4 is just 7x. I'd probably just leave it like that. There's nothing that I can really simplify this as. If I were to break it up, right, I'd have 7x over 7x minus 4 over 7x. So I'd have 1 minus 4 over 7x, which doesn't really clean it up particularly. So that's why I'm just going to write it like this. Now, for the domain, I think, yeah, for the domain of this thing, often, and I say often, because it's not always true, but often you can just look at the new function and figure out what the domain is from there, right? But that's not always going to be true. So what we should be doing, just to kind of cover our bases, and then we can confirm with our new function, right? So here it looks like x can't be 0, right? Because then I'm dividing by 0. So we need to keep an eye out for division by 0 and square roots of negative numbers. Here we're not dealing with any square roots, right? We've got division though, so we need to be aware of division by 0. So technically what we should be doing is we should say, okay, well, the domain for G is the set of real numbers, so there's no restrictions on G. However, whatever I put into f of x can't be equal to -4, right? And so no restrictions on G of x, but from f of G of x, we know that G of x cannot equal -4. Whatever I put into f can't be equal to -4. So then I have 7x minus 4 can't equal -4. Right? Now I can just solve for x here and say, okay, well, I can add 4 to both sides. So then I have 7x cannot be equal to 0, which is where we started just by looking at our new function, right? 7x can't be equal to 0. So, okay, fine. So then x cannot be equal to 0. So now our overall domain is the overlap of these two restrictions, but we had no restrictions heading in. So our only restriction here is that x can't be 0. So in terms of interval notation, we'll have -∞ up until 0. And then we kind of lift off ever so briefly at 0. And then we join back up at 0 again to infinity. Okay. So now we're going to do that same song and dance for the rest of the 3. And let me just check my work here. Okay, phew. It is the right answer. Let's do B. So now I have, when we're doing that, if we have -x plus 2 is greater than 0. You'll want to switch it because you'll have to talk about x. For the domains, you'll always want to talk about positive x instead of negative x, because otherwise it'll be confusing. Does that kind of make sense? Yeah, so you would need to switch the sign. So if you have -x plus 2 is greater than 0, you get -x is greater than -2, but then to ditch that negative, you get x is less than 2. I would always pick numbers, right? And just to make sure that that it still makes sense, right? So if I put, I'll pick any value that's less than 2, so that satisfies this end piece. So I'll do 1, right? And then if I put it in here, -1 plus 2 is greater than 0. Right? You can do, what if you did -3? Oh, but how embarrassing. 3 is not greater than or less than 2. Yeah, so much for the clarification. Hopefully it worked out. But yeah, so as long as you follow the rules, as long as you pick a value less than 2, it should still satisfy that. So you can always check it to make sure that it makes sense still. Yeah. Yeah. So let x be 3. No, doesn't work. Good. All right. So we're trying to find g composed with f. So g composed with f of x, I like to write it as g of f of x, which means f of x is going into g. So again, I like to replace the one inside with the function, and then I write out our new function. So I have g of x over x plus 4, I want to say. Yeah. Okay. So g was 7 times x, which in this case is going to be x over x plus 4. Now I can't remember what the functions were. 7x minus 4. Sorry, it's zooming back and forth here. So laggy. Okay, so to simplify this thing, I'm going to have 7x over x plus 4, and then I am going to make a common denominator. So I'm going to have minus 4 times x plus 4 over x plus 4, right? Kind of working with some fractions here. So this becomes 7x minus 4x minus 16 over x plus 4. 7x minus 4x should put me at 3x minus 16 over x plus 4. Can't simplify any further. So let me just check here. Phew. That is the answer. So again, right, we can have a look at our new function and just look at the domain. Like I said, usually that will work. Right here, x can't be negative 4. But technically, right, we look at the domain of f of x heading into this function, right? F of x, well, we have the restriction that x can't be negative 4. And then we need the overlap of x can't be negative 4 and the restrictions on g, but g has no restrictions. And so the overall domain, the domain is that x can't be equal to negative 4, or in terms of interval notation, we go up to, but not including negative 4, and then we pick right back up and go all the way to infinity. Let's do C. So now I'm composing f with f. So I'm stuffing f of x into f of x. So I've got f, oh, I guess I should write it out. F composed with f of x is the same as f of x, which is the same as f of x over x plus 4. So now I'm plugging x over x plus 4 into x over x plus 4. So you'll have to kind of keep your cool and be really careful when you're plugging this stuff in, right? So this becomes x over x plus 4. And again, I'm just going to show that this is one thing by wrapping some brackets around it. Over x plus 4 plus 4. Oof. Okay, so now I can simplify this. I need a common denominator down here, but other than that, I'm doing fraction over fraction, so I can flip and multiply. So here we go. I get x over x plus 4 over x plus 4 plus 4. I'll show them. Forcing a common denominator here of x plus 4. So I get x over x plus 4 over x plus 4x plus 16 over x plus 4. Now I've got a fraction over a fraction, so I can flip the denominator and multiply. And so I get x over x plus 4 times x plus 4, and I'll wrap those up in brackets to show that I'll be able to cancel those, over 5x plus 16, right? X plus 4x is 5x. Great. Can cancel. So then I'm left with x over 5x plus 16. Oops, there. Okay, so for the domain, I need to first make sure that I satisfy the domain heading into the function. So for the domain, right, f of x has domain x can't be -4, right? And then so overall f of x has domain that f of x can't be equal to -4, right? Which means that x over x plus 4 can't be equal to -4 either. To solve, so I want to solve for x, so I can move that x plus 4 over, so then I have x can't be equal to -4 times x plus 4. So now I'm just going to try to expand this and collect like terms and solve for x. So I get x is not equal to -4x minus 16. Solving for x, I'm going to add 4x to both sides, so I get 5x can't be -16. So then x cannot be -16 over 5. Which I'll just see if 16 over 5 simplifies. It does not, so it doesn't matter. But it's just something that I like to check, right? Because at least this calculator just does it for me anyways. So. Okay, so now the overlap of these two, right, is that, well, up here, x can't be -4, but also x can't be -16 over 5, right? So the overall domain is the overlap. So x can't be -4 and x can't be, -16 over 5. And just to have an idea of where that is, if it's less than or greater than 4, I'm not sure. So -16 over 5 as a decimal is -3.2. So it's closer to 0 than -4. So in terms of our interval notation here, right, I've got from -infinity, I go till 4, but not including 4. And then I pick right back up at -4. And then I go until -3.2, or I guess I should write that as I should do the exact answer. Negative 16 over 5. Oops. But not including negative 16 over 5. But then I pick right back up on the other side, negative 16 over 5. And then I'm in the clear to go till infinity. So that's probably the hardest one, right? As soon as you've got restrictions on the function that's heading into the new function, it gets a little bit messy, right? If you go back here, if you had just looked at the domain of the new function, right, you would have been missing that x can't be negative 4, right? And that's because we canceled these here. So that can happen. So just as a heads up, right, you want to look at, okay, what's my domain heading in there? And then what's my new domain as well? Okay, so just be careful. You'll want to catch them all, right? I guess you could look at before you canceled, right? Then you would be able to capture it all. But anyways. D. G of x. I get excited when I see something that has no restrictions on the domain, because if I'm composing it with itself, then there's going to be no restrictions right away, right? So it just makes it a lot easier. So we end on a high note here. G of x after that kind of probably the hardest one, right? F of x is G of x. Now I can't remember what G of x is. Is it 7x minus 4? I can't remember. Where did it go? 7x minus 4. Okay, phew. So that's going to be 7. Oh, sometimes you can write it either way, 7x minus 4. So what I was about to do was I was about to write 7g of x minus 4. You can do that too, right? You can write the outside function first with g of x instead of x and then replace your g of x. Doesn't matter. But I'm trying to keep it consistent here. Although when I do these problems, sometimes I jump around. Sometimes it feels easier. Yeah, no worries. Sometimes it feels easier to just kind of do the outside function first. But anyways, so then this becomes 7 times 7x minus 4 minus 4. If I expand this out, 7 times 4, that's the one I had to check. 7 times 7 is 49x, that's fine. Minus 28, and then minus 4. Negative 28 minus 4, just checking here. Okay, good. So I get 49x minus 32, which is what we had. There are no restrictions on G. Oops, combine those. No restrictions on G of x. Therefore, the domain is negative infinity to infinity. Keep it on the same page. Okay. Let's see here. Let's do one more question and then we'll take a little break. How about that? Although it feels like we should take a break now because David's gone. Yeah, let's do that. Let's have a break until 10. Oh, he's back. I was just planning a break, David. Sorry. You didn't miss anything. No surprises here.
Yeah, I was kind of charging ahead with the thing, so yeah.
Yeah. So, okay. Yeah, let's do one more question and then we'll have a little break. How about? Hey, this one's not bad. And I'm keeping it out. If you have questions, just stop me. We want to find the domain of a function. So we know that polynomials in general don't have any restrictions on the domain. That's fine. But now that we've got division, we need to make sure that this quadratic does not equal 0, right? And so for the domain, we need to make sure that x squared plus 2x minus 24 does not equal 0. So what I'm going to do is, because it's a quadratic, I can use the quadratic function to figure out where it equals 0, and then I'll pull those out. Okay. So here, this is a quadratic, so of course I can use the quadratic formula. So x is, and just as a reminder, I feel like we haven't done a ton of quadratic functions. If you did pre-calculus, then we did a lot of quadratic functions. But so here a is 1, b is 2, and c is negative 24. I'll move this down here. So x is negative b plus minus the square root of b squared minus 4ac over 2a. So negative 2 plus minus the square root of 2 squared minus 4 times 1 times negative 24 over 2 times 1. If you find that you have a negative under the square root, there are no solutions, which just means that you might have a situation like this, right, where it doesn't cross the x-axis, which is fine. That can happen. It happens a lot, right? So don't be alarmed if you find that you have a negative number in the square root. It just means it doesn't cross the x-axis. So we've got negative 2 plus minus 4 times 24 is 96 plus 4. So 4 minus negative 96, just making sure it is 100. I don't want to screw that up. And then, of course, we've got negative 2 plus minus the square root of 100 is 10 divided by 2. So at x equals negative 2 plus 10 divided by 2 and x equals negative 10 minus 10 divided by 2, this thing is going to be equal to 0. So those are the ones that we want to pull out. So x is 8 over 2, which is 4, and x is negative 2 minus 10 is negative 12 over 2, so x is negative 6. And I'll kind of write around it. At x equals 4 and x equals negative 6, the quadratic equals 0. So our domain is where x is not equal to 4 and x is not equal to negative 6. In terms of our interval notation, right, because we need to report it in interval notation, I've got negative infinity to negative 6, not including negative 6, picking right back up at negative 6, going to 4, and then having a little break, picking up at 4 to infinity. Good. Let's have a little break. Oh, say that again.
And here's where I point out that is actually fairly easy. You can just factor it.
Yeah. Yeah, so I mean, for me, I hate factoring. I hate factoring just by looking at stuff. If you're comfortable factoring it by kind of just head, totally fine. I always, so to factor a quadratic, I always just end up using the quadratic formula, unless it's like super, super easy.
Yeah, that makes sense.
Yeah. Yeah, I guess I should have looked at it. Anyways, let's have a quick little break until 11. Look, it's 11. All right. Let's keep going. So, hey, 5, not bad. But a graph to kind of an easy one to get back into it. We want to know if it's 1-to-1. First of all, I just want to highlight that we also know how to check if this is a function, right? Using the vertical line test. If it's 1-to-1, we have to use the horizontal line test if we just have the graph, right? And so it's the easiest way to check if you have a 1-to-1 function. And what you want to do is you want to make sure that a horizontal line only crosses this graph once. However, there are points here where two different values of x yield the same value of y, which by definition is not 1-to-1. Right, so not 1-to-1, since it does not pass the horizontal line test. Right. Remember, in order to have an inverse, the function has to be 1-to-1. We're not going to do those kind of big involved problems, but we are finding the inverse of a couple of functions here. And I decided to focus our efforts on exponential and logarithmic functions. I remember they're inverses of each other. And so first one we have to do is, okay, so we want to find a formula for the inverse. So there are kind of two ways that we could do it. First one is solving for x and then rewriting the variables, switching x and y, and then you have the inverse. Or I often switch the variables first because I always find it's easier to solve for y than to solve for x. I know it's the same, but in my brain, I just have an easier time solving for y. And I know that's weird, but I think the only steps that we went through in class were just solving for x. So let's go ahead and do that. So we have y equals e to the power of 2 minus x. So we want to solve for x, which is going to be f inverse of x, but then it's going to be in terms of y, but just kind of be a little bit flexible there. Maybe I'll just do f inverse. That's true. So if we're solving for x, right, I've got an x in the power. The only way to bring that down is to take the log, and often I'll take, so I always use ln. I always use the natural log, even if it's not base e, and then I do a little bit of work around that. But because it's base e, we should definitely use the natural log because then they cancel out, right? So if I take the natural log of both sides, ln of y is the ln of e to the power of 2 minus x. if we remember those log laws, then I have the ln of y here, but 2 minus x drops out. Technically, what happened is, right, we can bring that power down in front, and then you have the ln of e, which is just 1, right? So that's technically what's going on, but you just need to show the 2 minus x. And then solving for x, I usually add x over to the left-hand side because I don't like dealing with negatives, and then I subtract the ln of y over to the right-hand side. So I get the ln of y, kind of showing a lot of steps here. You don't have to show this many steps. You could have brought the ln of y over right away. But then the x is 2 minus the log of y. So then what we do is we swap x and y. So y is 2 minus the ln of x. Okay. So f inverse of x is 2 minus the ln of x. I have a feeling, though, that they don't want you to go that far. Let me see here. Oh, they do too. Okay, never mind. That's good. Great. But they just want to know, sorry, I shouldn't highlight that. They just want to know this part. Okay. So kind of same idea for the next one. Similar, I should say. But now we're starting with logs and then kind of undoing logs. Oh, I guess I cut that one. Never mind. But kind of, so this practice question, just remember that you could be given a function involving logs and then have to find the inverse, which would involve the exponential functions, right? So just be comfortable moving both ways. I don't know why I cut it. Well, there's only going to be one find the inverse function on the test, so maybe that's why I cut it. All right. Working with these log laws. Bob Lob's log. You guys seen Arrested Development? Anyways, yeah, log laws always make me think of that. Bob Lob's log.
I used to work for Loblaws.
Oh, really?
I do not have a high opinion of the company. Shopping at the store is great. Working there, no.
Yeah, it's a no. Yeah, I can see that. Yeah, I know it's tough. All right, back to log laws. Here we go. I want to express as a single logarithm. Of course, if you're given a single logarithm, you might be asked to expand it. So that would be the alternative type of question here. But again, I think usually I start and I make my practice test so large and long, and everyone gets kind of frustrated and scared. So I tried to keep it to the length of the actual test, so you'd have a good idea. But as we go through here, I'll kind of highlight some other alternatives. So in this case, right, the other option would be to expand from a single logarithm to something like this. Okay, keeping in mind the log laws, as long as you're working in the same base. So first thing I'm going to check is, do I have the same base? I do. I have base E. And so that's great. Even down here, right, I can go through and I can check both at the same time. I've got log base C, log base C, log base C. Okay, so now I can kind of forget about that because I'm allowed to combine these. Next thing I'm going to do is remember that if you're adding or subtracting logs of the same base, we are able to combine them, right? If we're adding, we multiply inside. No, they'll always have the same base, but it is something that you'll need to check in general. So on the test, no, they'll have the same base.
I've got a bit of a question.
Sure.
Yeah. And it actually is related to the last quiz. Do you, when like combining the logs and so on, is it always do the minuses first or the pluses first?
It doesn't matter. So yeah, so let's go through and do A, but it actually doesn't matter because multiplication and division kind of just like smushes together anyways. So you should be able to get the same answer regardless. Here, let's just go through and do A. So I'm going to write it out just so we have it because it's also on a different page. So 4 times the log of x minus 6 minus the log of x squared minus 10x plus 24 plus 2 times the log of x minus 4. First thing I'm going to do when I'm trying to zip these up, or at least in my mind I zip them up, is move these coefficients back up to the powers, right? So that's my next step here, is I'm going to have the log of 6 or x minus 6 to the 4th minus the log of x squared minus 10x plus 24 plus the log of x minus 4 squared. Okay. So now, right, I've got logs of the same base, and here, because I'm subtracting this one, it means that this value inside is going to be in the denominator. Because I'm adding here, it's going to be in the numerator. So this becomes overall the ln of x minus 6 to the 4 times x minus 4 squared over x squared minus 10x plus 24. I'm going to try to cancel some stuff here, right? And ideally, I would be able to find a factor of minus 6 and minus 4. Is it minus 4 or plus 4? Yeah. Hey, looks like, right, if I just look here and I'm trying to find factors of minus 6 and minus 4, that's what I have, right? If I want to add to negative 10, negative 6 and negative 4, do that. And if I multiply to positive 24, negative 6 and negative 4, do that as well, right? So I'm always looking for kind of the same factors as I have to cancel. X minus 6 to the 4 times x minus 4 squared. I'm going to rewrite that quadratic. You could use the quadratic formula, right? But we already found that it's x minus 6 times x minus 4. Which, of course, I can simplify this a little bit. So this becomes the natural log of x minus 6 to the power of 3 times x minus 4. I think we'll just leave it like that. You could expand inside, but that's what they've done, so call it there. Okay. Yeah, so it shouldn't matter because here I just kind of accordioned up. So I had this one is positive, this one's negative, so I did x minus 6 to the 4 over that quadratic, and then this one is adding, so then it goes in the numerator.
Yeah, I think I realized where I went wrong.
Oh, okay, nice.
Like, I might, because I think I did it so that I did like x minus 6 next to the 4 or minus the other one. and then waited to add in the third one, and must have lost something along the way.
Yeah. Yeah, that can happen. Just kind of be calm. All right, so we'll do the same thing with all these variables, right? But they behave the same way. So I have, because I'm not going to be able to keep it on the same page here. I'm just going to copy it out. B log base c of x minus d log base c of y plus log base c of z. Okay. Same deal, right? I've already checked to make sure I have the same base. So now I'm going to bring those coefficients up into the exponent. So then I have log base c of x to the power of b minus log base c of y to the power of d plus log base c of z. Pulling that log base c outside, x to the power of b is being added, right? It's positive, so I can put that in the numerator, and then y to the power of d is in the denominator, and then z is in the numerator because it's added. And there's nothing I can do to simplify here, so I'm done. I don't know if you have to write the log base c, probably, but you should be able to, it should come up with that function thing so you can enter the log base c. Okay, nice. Change of base formula is meant to be easy marks, so make sure that they are. Change of base formula says that the log base b of a is the same as the natural log of a over the natural log of b. There. So the log base 4 of 35 is the same as the ln of 35 divided by the ln of 4, which of course, as a decimal approximation, this is the exact answer, right? But it wants to 6 decimal places, so you have to kind of read and follow the label, so to speak. Ln of 35 divided by the ln of 4, roughly 2.56464158, but to 6 decimal places. 1, 2, 3, 4, 5, 6. So you'd have to round to 2. Oh, but I'm not going to do that because I want to keep it on one page here. And I'll run out of room. Log base 16 of 14, same formula, right? The ln of 14 over the ln of 16 is ln of 14 divided by the ln of 16, roughly 0.9518387,305. And then I'll just to 6 decimal places. But I won't do it. How confusing is that? Okay. do a first and then. So now we want to use logs or exponents or exponential functions to solve for x, right? And so what we want to do, right, is we want to kind of get rid of the log, because in this case it's wrapping up our x's and holding them hostage, right? And so to get rid of this log base 3, I have to raise everything to the power of 3 to make it cancel out. So if I have the log base 3 of x squared minus x minus 5 equals 2, to kind of shake that out, I have to take 3 to the power of log base 3 of x squared minus x minus 5. But what I do to one side, I have to do to the other side. And that's probably the kind of most common mistake that I see, is if you forget to do the 3 to the power of 2 on the right-hand side. But other than that, right, what's going on here is the reason we did that is so the x squared minus x minus 5 drops down. So I have x squared minus x minus 5. And what I'm going to do immediately is I'm going to bring that 3 squared, which is 9, over to the left and set it equal to 0. Minus 9 equals 0. Right, the reason I'm doing that is because I can feel a quadratic coming on, right? And so it's just easier if it's set equal to 0, we can use the quadratic formula. So -5 minus 9, -14, right? I'm just gonna double check. I don't want to mess anything up here. X squared minus x minus 14 is equal to 0. Without a coefficient, or with a coefficient of 1 on the x squared, you can probably talk yourself into, okay, well, what adds to -1 and multiplies to -14? I don't know, I'm just going to use the quadratic formula. That's hard. So here I can use the quadratic. So solutions here, x is -b plus minus the square root of, b squared minus 4ac over 2a. In this case, b is -1, so -1 plus minus the square root of -1 squared minus 4 times 1 times -14. Over 2 times 1. -14 times 4, I already had -14 on my calculator, -56. So 1 plus 56 is 57. Hey, no wonder I couldn't do it. 1 plus minus the square root of 57 over 2. Yeah, right. No one's going to think of that. Right, so then my solutions here are that x is 1 plus the square root of 57, which that's as simplified as it is, or it gets, over 2, and x equals 1 minus the square root of 57 over 2. There. So those are the solutions, and they've pulled the 1/2 out front, but it is the same, right? And then I trust that you'll be able to find the decimal approximation, right? So it wants the exact value in the decimal approximation to 3 decimal places. Right? So you'll want to pay attention because they keep mixing things up. But let's go and do B. We'll do the meat and potatoes, because I never thought we'd run out of time, but here we are. Not out of time yet, but. Now I have an exponential function and I want to solve for x. How do I bring something down from the power? Well, I have to wrap it up in a log. But in order to do that, first, I need to bring this 1 over, right? I need to isolate the exponential function before I can wrap it up in a log. So I get 1 plus e to the 3x plus 1 is equal to 80. But e to the 3x plus 1 is equal to 79, right? 80 minus 1. Now, if I take the natural log, right, I tried to use the same base, log base, as the exponential function. But for me in particular, even if the base was 4, I would still use the natural log and kind of deal with it. But what's nice about e is that the ln will cancel it all out. So e to the 3x plus 1 equals the ln of 79, which you don't want to forget about. The reason we did that is because they kind of cancel out. Right? We saw that earlier, right? You bring down the power and then the ln of e is just 1. So that's why it goes away. So 3x plus 1 is the natural log of 79. Now solving for x is breezy, right? Subtract 1 and then divide by 3. Good. And that's it. And again, I trust that you'll be able to find the decimal approximation. Here's the one that we were talking about earlier. We have to sketch this graph so something that satisfies each of these conditions. So what I want you to do is, and it might be useful to just kind of sketch it out and then look at the graphs or kind of work backwards. Either way is fine. We're checking in at x equals 0, at 8, and then at 0 and 8 again. In this case, some of these might change. Okay. So what I have is, as x approaches 0, right? So that's here. The limit of this thing is 4. So, but then we're also told that at 0, this thing is 6. So I'm going to draw an open dot here, and I'll pretend that that's at 4. But then I also have a closed dot here at 6. So if the limit overall at x equals 0 is 4, then what's this thing going to look like? Well, it might look like coming in here, take off again, right? And it doesn't matter what it looks like. You'll have to find one that kind of looks like this. But the overall behavior at x equals 0 should look like this, right? Open dot at 4, closed dot at 6. So then, let's see here. At 8, right, so at positive 8 over here, as I come in from the left, the limit is going to be 1. So let's make, so I know here, maybe it'll go like this or something like that. Call this 1. And then from the right, so now I'm coming in from the right, the limit, hey, I already did it. It seems to be around, so it's -3, right? So here, let's call this, well, my scale is terrible, but the idea is there. Okay. The function at 8 is -2. Okay, so that tells me that these two dots need to be open because at 8, it's actually -2. So here I'll put -2 here, and I'll do a solid dot, and then I'll go up with open dots at 8. Now I've incorporated all those conditions, so now it's a matter of finding a function that might look something like this. Of course, how these lines go, they'll be different, but at x equals 0 and at x equals 8, you have to have this behavior. Good. So 11. You had to do one right on quiz 3, this infinite limit. Okay. So we know from the domain x can't be -2, and yet here we insist on finding the limit as we approach -2 from the left, right? So as we're approaching from the left, these values are just slightly less than -2, but negative, right? And so up top here, how's this thing going to behave? Well, -2-ish plus 1 is -1-ish, right? And so this becomes kind of, think -1-ish. And I'm just kind of, because how you have to kind of justify these is just argue how this thing would behave as we approach -2 from the left. So if -2 from the left, so -2.1, -2.01, -2.0001, if we're adding 2, we're getting to small negative values, right? Because this is always going to be slightly larger negative than -2, right? So here, over a small negative, if we're dividing a constant by a really small number, and it keeps getting smaller and smaller and smaller and smaller, and it's a negative, we've got a negative over a negative. So overall, the limit of this thing is, therefore, the limit is positive. And so it's going to be positive infinity, right? Because as you divide a constant by a really small number, it becomes infinity. And then we just need to determine if it's going in the positive or in the negative direction.
All right. In that case, if it was like x plus 3 over x plus 2, x approaching limit of x approaching 2 negative, and that would be negative?
Yep. So here you're replacing this 1 with a 3. Yeah. Because then you'd have -2 plus 3, which would be positive, but this would still be negative. Exactly.
All right.
Yeah. Nice. Okay. Also meant to be easy marks, right? Because the first thing I do when I get a limit, okay, so evaluate the limit. First thing I do is I check, is this thing a polynomial? Yes or no? Tell me now. If it's a polynomial, I can just plug in the value, right? And so because this thing is a polynomial, right, it's just a straight line. I know a straight line has a domain of the set of real numbers, so I'm allowed to put anything in here. So x equals 4 is just as good as anything else. So here the limit becomes 8 minus 1/2 times 4, which is going to be 8 minus 4 over 2, which is 2, which is 6. Right? And that is because this is a polynomial. Since this is a polynomial, you don't need to explain this, but I do want to have it kind of explained in the notes. Since this is a polynomial, we can evaluate at x equals 4. And that's true for all polynomials. We did some version of all of these in class, right? And so I'm just kind of making sure that you know all those tips and tricks. So now we run into this problem where, okay, so as x approaches -5, but if you try to plug in -5 here in the denominator, goes to 0. Okay, plan B. What's my plan B? I'm trying to factor this thing so I can cancel some stuff out. If I'm able to manipulate this function, then I can find the limit that way. So here, the limit as x goes to -5 of x squared plus 5x over x squared minus 2x minus 35. It's going to be the same as the limit as x goes to -5 of x times x plus 5 in the numerator. And then I've got this x plus 5 here, so I'm hoping to be able to extract a factor of x plus 5. And here, this is one of those situations where I actually do see something that might work, right? 5 and 7. So if I have -7 and +5, it works out, right? So, but you absolutely could use the quadratic formula to find those factors, right? But here in this case, I see it. So I'm just going to go right there. So x times x minus 7 times x plus 5, right? Because I'm trying to match x plus 5 and x plus 5. That's my only hope at canceling here. And I'm just going to kind of mentally in my mind, as opposed to anywhere else, expand this thing out. So I get x squared. Okay, that's good. Plus 5x minus 7x. Okay, that's -2. Good. And then -7 times 5 is 35, or -35. Good. So now I've manipulated this thing. So I'm going to be able to take the limit as x approaches -5 of x over x minus 7. Now, all of a sudden, when I plug in -5 here, it doesn't change. I'm not dividing by 0, sorry. So I get, this is going to be -5 over -5 minus 7. -5 minus 7, just to make sure, is -5 over -12. 5 over 12. Good. Phew. That is the answer. Right, so step 1, check to see if you can factor stuff out. Step 2 is in the next question. Right, another way that we can manipulate these problems is by rationalizing either the numerator or the denominator. Crop this a little bit. There. So when I have a square root here, there's nothing I can really cancel, but as soon as I see a square root plus minus something, or something plus minus a square root, I can rationalize this to manipulate the function, right? And so that's going to be kind of your next thing. Okay, I can't factor anything here. I can't cancel this h. Okay, phase 1, okay, done. Or I guess plan 1. Plan 2, rationalize. Okay, here we go. So it looks like that's going to work, at least to kind of morph the function to something where I can just plug in h equals 0. Remember to rationalize the numerator in this case, right? Because the square root's in the numerator. I need to multiply by the conjugate radical, which is really just whatever is here on the left, and then the opposite sign, and then whatever's here on the right. So here we go. The limit as h goes to 0 of the root of 64 plus h, that's under the square root minus 8 over h, is the same as, so there I was just writing it out, as the limit goes to, of h goes to 0 of the root of 64 plus h minus 8 over h times, and then here I'll just show that I'm rationalizing by doing times the root of 64 plus h. So that value doesn't change. but then I have to add 8. So plus 8 and then over itself. All right, so notice the only thing that's changed here is that you're adding 8 now instead of subtracting 8. And once you expand this out, you'll see why it works. So this becomes the limit as h goes to 0 of the root of 64 plus h times the root of 64 plus h. That's just 64 plus h, right? The root of the root of x times the root of x is just x. And then we have plus 8 times the root of 64 plus h minus 8 times the root of 64 plus h. Oh, I gotta scoot this over here. And then negative 8 times positive 8 is negative 64 over h times the root of 64 plus h plus 8. Notice that I'm not expanding this h in the denominator out quite yet. A couple of reasons for that. I know I'm going to have to substitute in h equals 0 eventually. So if I'm multiplying by 0, that still doesn't help me. So I'm hoping to be able to cancel that. But also because it'll be easier once I can see how the numerator simplifies, it'll be easier to see how I can manipulate the denominator. Okay. Those middle two terms are going to cancel, right? That is the reason we use the opposite sign, right? So if you're adding 8, or sorry, subtracting 8, then you add 8 in the conjugate. And that's because these two middle terms are going to cancel out. So we get the limit as h goes to 0. And I don't want you to stop writing the limit. I know it seems kind of tedious, but we get 64 plus h minus 64 over h times the root of 64 plus h plus 8, not in the square root. Well, wouldn't you know it? 64 minus 64 is going to go away, but then in the same sweep, I see I'm left with h in the numerator and an h multiplying in the denominator. So those are going to go away to 1 as well. Phew, right? So then we have, I'll just kind of summarize this here, the limit as h goes to 0 of 1 over the root of 64 plus h plus 8. Now I can let h go to 0 and I'm not generating a negative in the square root. Okay, that's good. I'm not dividing by 0. That's good. So plugging in h equals 0 now is allowed. So I get 1 over the square root of 64 plus 0 plus 8. That's 1 over 8 plus 8, which is 1 over 16. Whew. All right. So we're just trying to manipulate these functions until we're able to substitute that whatever the limit is going to. Last question is a squeeze theorem. And then remember, I put a bonus question for the test. So the very last question won't be the squeeze theorem, it'll be the bonus. But you do have to do a squeeze theorem. I shouldn't make it sound like no squeeze theorem. Right? So this is where we ended off last day. And so if you want to evaluate some limit, so if you've got this kind of nasty trig function, especially cos or sine, right? Cos and sine are nice because they're bounded between -1 and 1. So we're going to leverage that and use the squeeze theorem. So here, use the squeeze theorem. So we know, so how I want you to do these is just start with the very core function, right? Whether that's sine or cosine, it doesn't matter. But we know that the cosine of theta, so we know just in general, the cosine of theta, so anything, cosine of anything, is between -1 and 1. So then what we do is we kind of step by step, we build up this function. So now I'm going to replace theta with 3 over x, but that actually doesn't change what it's bounded by, right? So now, so the cosine of office hours, yep, 3 over x is between -1 and 1 as well. So I'm just slowly trying to build up to that function that we've been given. Now, all that's missing, right, is this x to the power of 6. As long as I do it to both sides, right here, there was no theta to plug in 3 over x. So that's why we didn't manipulate the end bits, right? But now when I multiply by x to the 6th, I have to do it to all 3 sides. So now I'm going to have -x to the 6th is less than the cosine of 3 over x, which is less than or equal to x to the 6th. One thing that you should keep in mind is that x to the 6th, multiplying by x to the 6th is always positive. So you don't have to worry about the signs changing. So here, since x to the 6th is greater than, I guess, or equal to 0, the signs do not switch, right? If you had an odd power, then you've got some trouble, right? You need to consider the signs. But in this case, because it's positive, and I put it as a side note, it's not something that I need you to have in your work. It is something that later on we should probably have a good handle on, but this is just new for us right now. So just doing this is good for me. So now what I'm going to do is now, oh, and I forgot. Oops. I forgot to multiply it where it hurts, in the middle. Now I've built up the function that I want to find the limit of. So now to use the squeeze theorem, I'm going to take the limit of all 3 of these regions. So I want the limit as x goes to 0. So the limit as x goes to 0 of -x to the 6th, just by limit laws, that's going to be less than or equal to the limit as x goes to 0 of x to the 6th cos of 3 over x, which is less than or equal to the limit as x goes to 0 of x to the 6th. Well, here, this is a polynomial, right? -x to the 6th as well as x to the 6th. I'm just allowed to plug in x equals 0 here. Okay. So then 0 is less than or equal to, notice that we don't even have to do anything with this middle limit, right? Which is really nice. The limit as x goes to 0 of x to the 6th cos of 3 over x is less than or equal to 0 by the squeeze theorem. And you should say by the squeeze theorem or by the pigeonhole theorem, or there's a couple of names. We've called it the squeeze theorem. But if the limit is locked between 0 and 0, well, there's only one option for it to be. So therefore, by the squeeze theorem, the limit as x goes to 0 of x to the 6th of the cosine of 3 over x equals 0. We did it. We spent too much time in the beginning, but because I'm able to kind of talk around each question and we still managed to finish, I think we're going to be good for time, or you'll definitely be good for time for the test. So I'm happy about that. Any questions before we go?
None that I can think of right now.
Cool. I do have office hours, but I know they're kind of, I don't know, you probably have other classes, but so you can pop by my office hours, or if you do have any questions, just let me know and we can meet whenever. So not to worry.
All right then. I'll see you Friday.
See you Friday. Oh yeah, during the test, I'll be here if you have questions, just like the quiz, but you don't have to be in here if you don't want to. See ya.